Alright, Unit 4. Unit 4 is a short unit with lots of memorizing. We'll break down what's important here. So the first thing to know is that plants make sucrose. We do not. So we'll take care of that one right now. Only thing to really know out of the first couple slides when he's just talking about making sugar in plants is pretty much glycolysis backwards. Just watch out for any sort of reactions that look like some sort of fructose plus some sort of glucose going into sucrose. That's not a reaction we can do. Sucrose synthase is not something we have. So a lot of times he'll list a couple reactions and say which is not found in humans. Look for the one where it's going the other way towards sugar. There's a little bit on lactose, how it's synthesized and how it's regulated, and then most of the unit is bringing 3 other sugars into the glycolysis we already know. So we'll take a look at the lactose synthesis first. Before we synthesize the lactose, it's basically saying that when you have galactose in your system, it's good for a couple things. One of them is for energy, which we're going to see later, and the other one is to be part of membranes. And the reaction to associate with membranes is an activated galactose plus N-acetylglucosamine. And the enzyme for that is galactosyltransferase, and then you get galactosyl N-acetylglucosamine. So that's the thing that you're going to find in the membrane itself. So that's for non-lactating, so most tissues are going to do that. For lactating tissues, you take that activated galactose, add a glucose, and you're going to get lactose. Thing to know about lactose synthase is that it's a 2-part enzyme. Part of it is this enzyme here from the membranes. That's called the galactosyltransferase. And the other part of the enzyme is a alpha lactobulmin complex. There's been questions in the past about what is a 2-part or multifunctional enzyme. Lactose synthase is one of them because there are 2 separate things making up lactose synthase. Throughout this unit, anytime you see UDP, I'm going to use the word UDP and activated interchangeably. Which means the UDP makes it ready for the next enzymatic step. So the next thing in the slides, you're going to see a slide that says lactose precursors, probably not. It's a theoretical pathway that doesn't really exist in humans, so I just didn't bother memorizing it. The only thing that could be asked is one of those reactions, and it will say, does this happen in the human body or not? And I memorized the lactose precursors, the one that says probably. And that took care of knowing which one happens and which one doesn't. So I would just learn what we're going to take a look at here. Just know this really well, how you actually make lactose. So it starts off just the same as glycolysis does. It goes from glucose to glucose 6-phosphate via hexokinase. And then another enzyme that's going to become very popular, so learn it now. I always abbreviate it PGM. Phosphoglucomutase. Phosphoglucomutase takes the phosphate on the 6th carbon and moves it to the 1st carbon. So now you have G1P, and the enzyme that we're going to use next is UDP glucose. Pyrophosphorylase. ran out of room there. Pyrophosphorylase. So the UDP glucose pyrophosphorylase makes UDP glucose. From that UDP glucose, we're going to make it into galactose, which is the epimer. So the enzyme is called UDP glucose epimerase. So now we're back with where we were before with an activated galactose. So we're going to pull in another glucose molecule somewhere, bring in our friend lactose synthase, and you have lactose. You also have a free UDP, but nobody really cares about that. So that's the pathway I've memorized. So once you know this pathway, you won't need to know the theoretical pathway because you'll have this one down. The regulation of this pathway is very simple. Progesterone inhibits and prolactin stimulates this. Prolactin stimulates lactose. Very easy to remember. It stimulates it by increasing the amount of the alpha-lactalbumin in the mammary glands, and because you have more of that, you're going to make more lactose synthase, because lactose synthase is composed of the alpha-lactalbumin and the galactosyltransferase. So it's one pathway to memorize with lactose, and that's all we're going to do with it. The rest of this unit is taking a look at glycolysis again and figuring out where the three other sugars enter. So fructose can enter in two places. Most commonly is the liver, and less commonly from a few places, but the one he always uses is adipose. So that one comes from the fat. The other ones he listed as the muscles, the testes, the retina, but that's not as important. Adipose is always the one listed. So the fructose from the liver has some new enzymes here to learn. First one is fructokinase. Instead of hexokinase, fructokinase, so FK. And if it's not hexokinase, it's always going to put the phosphate on position 1 here. So fructose, it's a kinase, so plus ATP, puts its phosphate on the 1 position. You have another fructose 1-phosphate aldolase, also known as aldolase B. Remember, the aldolase takes the fructose and combines it into, or breaks it apart, cleaves it into 2 separate metabolites. So one looks familiar, DHAP. DHAP goes to GAP by the enzyme we knew from glycolysis. Reaction number 5, which is TPI. And then the new enzyme takes glyceraldehyde into GAP by another kinase, triose kinase. Let's see, since I'm doing this one in blue here, the first pathway we learned was fructose from the liver, and that goes through a series of reactions and enters glycolysis at this step. Most notably, the important thing to know about this is that it skips PFK1, or it skips reaction 3 that glucose goes through. So insulin is not stimulated. So you don't feel full when you're taking lots of fructose in. So when the commercials that say high fructose corn syrup is the same as glucose, this is how you can explain that they're lying. So fructose from the adipose tissue is the same enzyme as glucose. The first step in glycolysis is glucose, hexokinase 1. So it takes fructose to fructose 6-phosphate. So that one is very easy. Let's see, I was using green for that. So the next feeder pathway is fructose from the fat. And through just one reaction, you end up at fructose 6-phosphate. Alright, Manos is another easy one. So if we're starting with Manos, to get to Manos 6-phosphate, we're going to use hexokinase again. Remember, hexokinase puts it on the 6th position, fructokinase or galactokinase is going to put it on the 1 position. So to get from Manos 6-phosphate to fructose 6-phosphate, I'm going to use a new enzyme specific to this reaction. It'll never come up anywhere else. Phospho-Manos isomerase. So in 2 reactions, we can go from Manos here into fructose 6-phosphate. So there could be a question there, which 2 sugars enter in at the same place, Manos and fructose, as long as it's coming from the adipose. The last one to learn, which is a little more complicated than the other ones, is Galactus. So the first step, you have an enzyme called Galactose kinase. Galactose kinase puts the phosphate in the 1 position. You're going to add an activated glucose. And the enzyme for that is just called transferase, because the name is really long, galactose 1-phosphate uridyl transferase. And what that enzyme does is switch the UDP and the 1-phosphate here. So here galactose has the 1-phosphate, and here glucose has the 1-phosphate. And the UDP switches as well. So to get into glycolysis, you take this glucose 1-phosphate, and we're going to turn it into glucose 6-phosphate. And that's done by phosphoglucomutase, the enzyme that's just going to keep coming up again. And you're glucose 6-phosphate, so you're into glycolysis. Let's come over here. Try to keep my color coding. Galactose, through a couple of reactions, goes to glucose 6-phosphate. There's one more thing to know about this reaction, is that you're here with this UDP galactose that's left over. You've already shipped the glucose off to glycolysis, so you're going to take that activated galactose and change it to a activated glucose. And you do that by UDP galactose 4 epimerase. It sounds like a lot, but just remember glucose, or galactose and glucose are epimers on the 4th carbon. So that basically just switches galactose into glucose. So now you have this activated glucose, which I think of as being recycled into the second step up here. So that's where that UDP glucose came from. So then another galactose will enter, the same reaction will carry off every time you ship one glucose molecule off to glycolysis, and you switch your leftover galactose back into an activated glucose and keep recycling. There are disease processes associated with this one. So each enzyme, if there's a deficiency in any of them, it's going to be a form of galactosemia. Enzyme 1, galactokinase, will result in cataracts in infants. Enzyme 2, the transferase, is the most serious one. Poor growth, poor liver development, mental speech issues, death is very common, and this is when they screen for at birth. And the epimerase is the same as number 2, except less severe. So those are a few things to know about galactose enzyme deficiencies. The last thing to note on all of these is the yield is the same as glucose. So with glucose, if we took 1 glucose, we would get 2 pyruvate. If we get a fructose, a galactose, or Manos, fructose no matter where it's coming from, you're always going to end up with 2 pyruvate at the bottom. So the ATP yield is going to be the same no matter what sort of sugar you're coming from.